I'm Matt Campbell, and I'm here today to talk about GUI accessibility across platforms and programming languages using Rust, and in particular, an open source project called AccessKit. So, what is AccessKit? It's a cross platform library that GUI toolkit developers can use to make their user interfaces accessible to blind people with screen readers, low vision, people using screen magnifiers, plus people with various other disabilities using other assistive technologies. Rust GUI development is quite active right now. Several different architectures are being tried, different implementation approaches, different graphics technologies, and so forth. And we want to make sure that all of these different GUI toolkits are accessible. But there's a lot of incidental complexity in making a GUI accessible because of the various platform-specific accessibility APIs. And these platform-specific APIs use platform-specific technologies such as the COM, the Component Object Model on Windows, Objective-C on Mac OS, dbus on what we often call desktop Linux, or more generally other Unixes, and so on. So AccessKit provides an abstraction layer over these accessibility APIs. It's currently usable on Windows and Mac OS. We have our Unix platform adapter under development, and we've got more platforms to come. And it's written in Rust, but it can also be used from other programming languages, and I'll be talking a little more about that later. So without further ado, I'd like to play my first demo. And for this demo, I'm using the Hello World example program that comes with the eGUI toolkit. eGUI has had integrated support for accessibility using AccessKit for the past several months now. And this demo is going to use the NVDA open source screen reader for Windows, as well as the Windows built-in screen magnifier, and another Windows accessibility feature called text cursor indicator, which makes it easier to see where the caret or text insertion point is on the screen. So this will show how implementing accessibility with AccessKit enables multiple accessibility features. First, let's see what happens if the GUI toolkit doesn't implement accessibility. Here is the eGUI Hello World app with AccessKit turned off.
My eGUI app.
I'll start using the tab key to move through the window. The screen reader isn't saying anything. The screen magnifier is magnifying a portion of the screen, but it's not dynamically adjusting which part of the screen it's showing based on focus and text cursor position as it normally would, and the enhanced text cursor indicator is not showing. Let's see if the screen reader can read anything in this window.
My eGUI app.
And it cannot. Here is the same app with AccessKit enabled.
My eGUI app window.
Now I'll press the tab key to move to the first control in this window.
Your name. Edit Arthur.
I can move to the beginning of the edit control with the home key.
A.
Select what's currently in there.
Arthur selected.
Delete my selection.
Blank.
The screen reader is giving feedback as we go. Now I'll type my name instead.
M. A. T. T.
Up to this point, all of the key presses that I've done have been handled by the application and specifically by the eGUI toolkit. Now I'm going to use a screen reader command to read the current line.
Matt.
Now I'll press tab to move on to the next control.
H slider 42.
And I can move that slider back and forth with the arrow keys.
43. 42. 41.
And again, those keyboard commands are being handled by the GUI toolkit. Let's tab forward a couple more times.
H spin button 41. Click each ear button.
This time I'll use a screen reader command that will programmatically activate the button using the accessibility API.
Invoke.
And finally, I'll use another screen reader specific keyboard command to read the next item in the window, which cannot receive keyboard focus.
Hello Matt, age 42.
And that is, in fact, my current age as of this recording. So there's my first demo. Now, I'd like to clarify a few things after that demo. I realize I might have made it look a little too easy, as if it was just a matter of turning AccessKit on. While it's true that AccessKit clears away or aims to clear away all of the accidental complexity I was talking about, it still does leave the essential complexity of making a UI accessible, which mainly amounts to exposing information about the content and structure of the user interface. And I'll go into a little more detail about what that looks like. But the upshot is that there is still some work required in GUI toolkits such as eGUI to be accessible, but at least we hope that it's much less than it would have been before. There's also more to accessibility than what AccessKit itself can help with. As I mentioned during the demo, it's the responsibility of the GUI toolkit to implement certain keyboard commands, such as tab and shift tab to move the keyboard focus. GUI toolkits also need to deal with some other things, such as supporting different color schemes. And of course, a lot of people are already doing that for light versus dark mode. And the reason for that last point is that AccessKit is completely decoupled from the graphics or the visual output of the GUI toolkit. So implementing AccessKit will not by itself have any effect on what a sighted user sees from the GUI toolkit. The effects that you saw during the demo were implemented by the Windows accessibility features that I had enabled. It also doesn't matter what graphics API you use to render your GUI, whether you use Vulkan, WGPU, Direct3D, Metal, whatever. You can make your GUI accessible with AccessKit. And to drive that point home, I'm now going to play my second demo, which is a prototype of making a simple choice-based narrative game that uses the Unity game engine accessible with AccessKit. And for this demo, we took an existing open source game that was provided by a company called Inkle Studios that they put together to demo their narrative scripting engine, and we made this game accessible with AccessKit.
The Intercept window. Inkle presents.
First, we have the title sequence.
The Intercept.
And now the story begins.
They are keeping me waiting.
We need to press a button to continue, so I can press the tab key to move the keyboard focus.
HUD 14 button.
And press enter.
The Intercept window. HUD 14. The door was locked after I sat down. I don't even have a pen to do any work. There's a copy of the morning's Intercept in my pocket, but staring at the jumbled letters will only drive me mad. I am not a machine, whatever they say about me.
Now we have our first real choice in the story, so I'll press tab again.
Think button.
But wait, what did it say right before that? I can use a screen reader command to review the text on the screen.
I am not a machine, whatever they say about me.
And so on. You get the idea. So that is my second demo, and by the way, for that demo, I was, again, using the NVDA screen reader, but not the other accessibility features. So before I talk about the AccessKit architecture and what makes it distinctive, I want to give a little background information on how accessibility, on how a user interface is made accessible. And the central concept here is what we call the accessibility tree, which is a hierarchy of nodes that provide information about the content and structure of the user interface. And here we have an example accessibility tree, well, a partial example loosely based on the eGUI application from the first demo. The root node is the window itself. Then we have a static text, which is the title of my eGUI application at the top of the window. Note that's distinct from the title bar of the window. That is normally handled, well, by default, handled by the platform. Then we have the label for the your name text input control. And the relationship between the label and the control is indicated by the labeled by property on the control itself. And then under the control, we have a child node, which is what we call an inline text box. For a multi-line text input, there would be an inline text box, basically, in the simple case, for each line of text, and that can get a lot more complicated. I won't go into a lot of detail about that. I also show that the inline text box node has the widths of each of the characters, although I didn't include the actual character widths here for brevity. But that information allows things like the Windows screen magnifier and the text cursor indicator to know where the text cursor is on the screen, as well as knowing where any given range of text is located on the screen. So that is just a quick overview of what an accessibility tree is made of, so that some of the other things that I'm going to talk about will make a little more sense. So now I want to talk about what I think is the most distinctive feature of AccessKit, and that is what I call the push-based architecture. And this is in contrast with the platform accessibility APIs that AccessKit is implementing. And those APIs are pull-based, which means that the implementation, so it's basically all callbacks, where an implementation like AccessKit would more or less provide a callback function for each property of those accessibility tree nodes that I was showing you earlier. And the assistive technology, such as a screen reader, would typically, through inter-process communication, keep calling into that API to query certain properties. But the architecture that AccessKit implements is adapted from what Chromium does internally for its accessibility. As you may know, Chromium has a multi-process architecture where you've got a main browser process and then one or more sandboxed renderer processes. And those processes communicate asynchronously. But the pull-based platform accessibility APIs that I was just talking about are synchronous. So when one of those APIs is called, and that call is handled by the main browser process, that process has to have the information there already. It can't go ask the renderer process for it on the spot. So what Chromium does, and what AccessKit also does internally, is, well, in the case of Chromium, the renderer process pushes either a full accessibility tree up front or incremental tree updates later on to the main browser process, so that information can be right there. And likewise in AccessKit, the GUI toolkit pushes full trees or tree updates to what we call the AccessKit platform adapter, which is the component that actually implements the accessibility API. And I think that this push-based approach is the right way to do accessibility, because it means that an accessibility tree update is analogous to a frame of visual output in the GUI. So just as GUIs render, I mean, they're basically pushing to the lower level graphics layer with each frame. So now they can push accessibility tree updates as well, and it's a more natural fit for current GUI architectures. And it's especially a natural fit for a particular class of GUI toolkit called an immediate mode GUI. And the eGUI toolkit that I showed you earlier is one such example of an immediate mode GUI. And I won't spend a lot of time talking about that, but basically, in an immediate mode GUI, um, the the full frame is redrawn with every for every frame. The UI is redrawn more or less from scratch, and immediate mode GUIs don't tend to maintain a lot of state about the UI across frames. So it would be awkward for an immediate mode GUI to directly maintain a tree of accessibility objects and implement the callbacks that are required by the platform accessibility APIs. But with AccessKit, a toolkit such as eGUI can push a full accessibility tree with every frame, and the AccessKit platform adapters, as well as another glue layer that I'm going to talk about shortly, make sure that the platform accessibility APIs only get events about the parts of the tree that actually changed. So, as I've mentioned, there's a bit of an impedance mismatch between the pull-based approach of the platform accessibility APIs and the push approach that AccessKit uses that's such a good fit for immediate mode GUIs in particular. And to bridge that gap, we have a component that we call the AccessKit consumer crate, because it consumes the tree updates being pushed by the toolkit. By the way, AccessKit is a multi-crate project. We currently have a monorepo. And this crate is not used directly by GUI toolkits or applications. It's used by the platform adapters, which are the crates that implement the accessibility APIs. And the consumer crate provides a pull-based query API that is similar conceptually to the platform accessibility APIs, so that that simplifies the task of implementing the platform adapters, because the glue that's needed to bridge those two approaches is implemented in just one cross-platform place. The consumer crate maintains an in-memory structure for the accessibility tree and applies the tree updates that are being pushed by the toolkit to that structure. And as it is processing those tree updates, it runs callbacks on the platform adapter to let it know about which nodes in the tree have been added, changed, removed, when the focus moves and stuff like that, so that platform adapters can use that information about what has changed in the tree to raise platform-specific accessibility events. So now that I have talked about the push-based architecture, I want to spend a little time talking about a particular problem that this architecture helps us solve, and that is the bottleneck of the UI thread. The UI thread in a GUI is the one thread that handles events from the platform. Keyboard input, mouse input, touch input, changes to window position and size, some other things, and most importantly for our case, by default on most platforms, and by necessity, unfortunately, on a few platforms, the UI thread is also the thread that receives all of those queries from assistive technologies about accessibility. And in a lot of cases, those, in order to handle, for instance, a single screen reader command, or to respond to a single event such as keyboard focus change or the movement of the cursor, a screen reader or other assistive technology needs to perform several queries on the accessibility API to gather all of the information it needs. And while some platforms have ways of optimizing this, those queries can very often amount to several round trips of interprocess communication, or IPC. So that means that if the UI thread is busy doing other things, and it can't handle all of those repeated requests immediately, then a screen reader is going to feel sluggish. And similar concerns also apply to other assistive technologies. And I think a good way to think about what that is like is imagine if the screen went blank whenever an application, whenever the UI thread of an application was busy or hung. That is more or less what it's like for a screen reader user. As a sighted person, you can still see what was last drawn to the screen, even if the application is busy and doesn't respond to you immediately. But a screen reader user is entirely dependent on being able to get the information that they need out of the screen reader, and the screen reader in turn needs to get that information from the application through the accessibility API. So here is how AccessKit, oh, and I forgot to mention, while I don't have a realistic demo of the problem of a sluggish screen reader due to the UI thread problem, trust me, it is a real problem that affects even well-funded commercial applications. And it was, when I was on the Windows accessibility team at Microsoft, it was something that we spent quite a bit of time on. So how does AccessKit deal with this problem? The first thing that helps us, of course, is that Rust enables safe concurrency. The freedom from data races, the type system features that allow us to protect things behind a mutex or read-write lock and be sure that those locks are going to be acquired, the mutability rules. And of course, a lot of us already know all about those things, and it's often been said that Rust enables fearless concurrency. And so this enables accessibility API implementations such as the AccessKit platform adapters to confidently take advantage of multi-threading in a way that the vast majority of accessibility implementations have never done, even on platforms that theoretically allow it. But the other thing that helps us deal with this problem is AccessKit's push architecture, because it means that the platform adapters rarely need to call back into the GUI toolkit. There is one thing that does require callbacks, and that is if the user specifically requests an action through their assistive technology, such as at the end of my first demo when I used a screen reader command to invoke one of the buttons. Those kinds of actions need to be handled through a callback, but those callbacks can run asynchronously. The really important thing is that AccessKit doesn't have any synchronous callbacks that need to run and return a result, because the push architecture makes that unnecessary. Now, unfortunately, not all platforms allow us to take advantage of this possibility of concurrency. For instance, Mac OS accessibility requests are still bound to the UI thread, and the same is also going to be the case on iOS. But on Windows, for instance, most accessibility operations can run away from the UI thread, the notable exception being the initial request for the root of the accessibility tree. And on desktop Unix platforms using the ATSPI protocol over dbus, AccessKit's implementation of that protocol is fully independent of the UI thread. So even if the UI thread is completely hung, as long as the process itself is still running, a screen reader user, for instance, can still find out all about the latest contents of the accessibility tree as of the last pushed tree update using their screen reader commands, so they can find out what was on the screen before the thread was hung or hopefully only temporarily busy. So that is an overview of what I believe is a significant advantage of AccessKit's architecture. So now I'd like to talk a little bit more about the bigger picture beyond the core architecture, and I'll start with language bindings. First, AccessKit has C bindings released right now. Well, they actually have been released for a few months now. We use cbindgen to generate the header file, and we now have a cross-platform example that uses SDL for creating the window and handling input. And by the way, that example also shows how to use the Access Kit C bindings in a project that's built with CMake, again, across platforms. We are currently working on Python bindings using Pyo3, and again, we have a cross-platform example using Pygame, which in turn is a wrapper over SDL. We have Java bindings under development. They're very incomplete so far, but they're already being used in a real-world project. I showed you our Unity demo. We may be looking at rewriting the C# bindings that we have for now, but right now that particular implementation is based on sending JSON serializations of the Access Kit tree updates across the FFI, foreign function interface layer. In the future, we'd like to do bindings for C++ and Go as well. And of course, we welcome language bindings from others in the community. So what's next for Access Kit? Well, we need to support more types of widgets, including list views, tree views, tables, menus, and a handful of others. We have a lot more work to do on our Unix platform adapter to bring it up to par with the Windows and Mac OS adapters, particularly when it comes to supporting text editing, as I showed in the first demo. We are beginning to develop other platform adapters, Android, web applications that render their UI to a canvas, and we plan to develop an iOS platform adapter as well. And finally, we would like to, well, we know we need to do a lot of work on documentation, because we realize that most toolkit developers that would like to make their GUIs accessible are not themselves experts in accessibility. So we need to provide clear explanations of the concepts and a roadmap from zero to accessible toolkit. Beyond that, there are a few more exploratory areas I would like to work on. I'll just cover these very briefly because I know I'm running out of time. I'd like to implement an embedded screen reader where text-to-speech output is built directly into the application. This approach is often called self-voicing. This could be useful, for instance, for games running on game consoles and other environments where there is no platform accessibility API. I want to experiment with applying the push architecture all the way to pushing tree updates to the screen reader or other assistive technology. And I think that would be a good way of completely solving the latency problem that I was talking about earlier, getting rid of the overhead of IPC round trips. And finally, accessible screenshots. As I alluded to earlier, the Access Kit tree structure is serializable. So imagine if an image file could automatically include a serialized version of the accessibility tree so that a screen reader user could explore the full richness of content and UI structure that was there in the image, as opposed to simplified alt text or alternative text. So how can the community get involved? Well, first of all, if you're developing your own GUI toolkit, please consider making it accessible with Access Kit. And as you do that, I mentioned that we still have a lot of work to do on documentation. If you would like to contribute directly to the documentation as you go, that would be great. But if not, at least please feel free to ask questions. Language bindings, as I mentioned earlier, the more the merrier. We can also always use help with infrastructure and maintenance tasks, such as improving our continuous integration pipeline or helping us keep dependencies up to date. We've already had a few contributors help us with that. And finally, funding for future work on the project. I personally have a GitHub sponsors page, which I will link to at the end of the talk. As I come to the conclusion of the talk, I'd like to offer a few special thanks. First of all, my colleague and our primary volunteer contributor to this project, Arnold Lubria, and he is here at the conference today. And he approached me 2 years ago because he was starting to work on an accessibility project of his own that was going to be similar in goals to AccessKit, but he figured out that I was doing some work on accessibility using Rust, and he asked if we could team up, and I'm glad that he did. It's one of those chance online meetings that really make a lot of difference. I'd like to thank Google for funding most of my work on AccessKit so far, and especially the Google Fonts team. And finally, I would like to thank everyone that has worked on Rust itself for making this project feasible, because Rust is a safe systems programming language. It enables us to provide this reusable infrastructure for Rust GUIs themselves, but also for other programming languages. Arnold has told me that he wouldn't have even attempted a project like this in C or C++, and I feel that while I maybe could have done something like this in C++, it would have been less robust and certainly not developed as quickly. So in conclusion, we can have nice GUI toolkits. And this, of course, is a variation on the saying that has often been said about Rust, which is that we can have nice things. Rust is known for bending trade-offs, the most famous one being safety versus speed. Well, when it comes to GUI toolkits, there has been a dichotomy for a long time between the handful of mature toolkits, or in particular web browser engines that implement accessibility well on the one hand, and the variety of GUI toolkits with different architectures that are more finely tuned for their application niches on the other hand, but don't implement, for the most part, don't implement accessibility at all. And now with AccessKit, we are working towards making it possible to have both a variety of different styles of GUI toolkits that are well suited for their application domains and just the preferences of their developers, but that can also take advantage of mature shared accessibility infrastructure that has never been possible before. So we can have nice things with Rust, and now with AccessKit, we can have nice GUI toolkits. And there is the link to the AccessKit website, my email address, and as I mentioned, the link to my GitHub sponsors page. Thank you.